Now that we have learnt about packet switching, let's see how it applies in practice through Ethernet switching. But before that, a quick quiz. So here is what we have learnt so far. Switching helps scale networks, providing a star topology. Packet switching is a form of switching that utilizes resources better than the alternative, which is circuit switching. And within packet switching, datagram switching is the most predominantly used mode of switching. Internet, for example, applies datagram packet switching. So in this video, we will examine how packet switching helps interconnect Ethernet segments. The devices that do switching at layer 2 are called bridges, also called layer 2 switches. So here this bridge is interconnecting two Ethernet segments, thereby extending the local area network. So that is why this is called extended LAN. So there is LAN 1 and this is LAN 2, and by interconnecting them now we have one big extended LAN. So this bridge has multiple inputs, multiple outputs. In this case it has 2 inputs and 2 outputs, but in general it can have multiple inputs, multiple outputs, and these are called ports, input ports and output ports. I have talked again and again about one reason why we may want to use switches, basically to extend the span of the network, because there are load or length restrictions as part of a given LAN. For example, in Ethernet 10BASE-T, you can't go beyond 500 meters, and also there is a restriction that you can't connect more than 1024 hosts on a segment. Can you think of any other reason as to why we may want to use switches? There could be administrative reasons. For example, this LAN segment may be administered by the CSE department and this LAN segment may be administered by the EE department. Even if load and length restrictions are being met, it is preferable to use a bridge to interconnect them, just because the CSE department may want to manage its own host and EE department wants to manage its own hosts. Also, the bridging can help in security by isolating the networks. If something is going wrong, a security attack is happening, this can potentially be isolated from what's happening on the other LAN segment. Now that we are convinced that bridging is useful, an important functionality that we need to address is the following. How do you forward packets? Suppose host A is sending a packet to host B. So this packet is being received by this bridge on this particular 0. What should it do with this particular packet? Drop the packet, because host B is also on this particular LAN segment itself. Similarly, if host A were to send a packet to host E, ideally what should this bridge do? Since host E is on the segment that is connected through its port 2, it should take that packet and send it out on port 2 and not on port 1. One could potentially configure all this as part of this particular bridge. But this manual configuration can be rather tedious. When new hosts are added, you have to again reconfigure the bridge, and when hosts are removed, again you have to reconfigure the bridge. So automatic is always good. Humans are known to be error prone. So what is one very simple thing the bridge can do to ensure that the packets reach the intended destination? Note that this need not even be efficient. So here is what it can do. Whenever it receives a packet on a given port, you just send it out on all the other ports except on the port in which it was received. For example, when host A sent a packet to host B, it received it on port 0. You send it out on port 1 as well as port 2. The same applies when host A sends a packet to host E, comes on 0, send it out on 1 and 2. In the first case, where host A is sending to host B, this forwarding on 1 and 2 is rather wasteful, because host B is already on the same segment, but that's okay. It's not going to produce an incorrect result. Host B is still getting its packet. It's not efficient. Similarly, host A sending to host E, it should only go on 2 and not on 1. Again, that's okay, because host E is getting the packet still. It's just that it is inefficient. Now the question is, can we do better than this? Can we make the forwarding more efficient, where the packet is only forwarded on that port which makes sense? And to do it in a way that doesn't involve manual configuration of this particular bridge. A bit tricky, but I think you can do it. The hint is make use of addresses. So here is the idea. It's a very simple idea, but a very clever idea. Is what you do is you inspect the source address of frames that are passing through you and map that particular address to the port on which the frame was received. For example, when host A sent a packet to host B, this packet is going to be received on this particular bridge on port 0. In which case this bridge is now going to have put an entry that says host A is on port 0. Note that you are looking at the source address here, not the destination address. So to build the forwarding table, you are using the source address, but to forward a particular packet, you will use this table to forward the packet. So another thing that you do is whenever you make an entry like this in the forwarding table, such a table is called the forwarding table, after some time you are going to purge this entry. In other words, you are deleting this entry. Why would you want to do something like this, purge it after some time? Well, it's conceivable that someone may have removed this host A from this segment and connected it in here. In which case, if this entry was permanent, then host A will not get any packets from others. Now, this thought must have occurred to you. Suppose host B never sent a frame so far, so you have never seen a frame from B, thereby you don't have an entry in the forwarding table, but host A has sent a particular frame for host B. What do you do in this case? Well, what can you do? You don't know the information, so you are going to forward it on all of your other interfaces. So here is the algorithm. If a frame is received at a bridge for destination D on port P, this is what you do. If there is no entry for D in your forwarding table, you forward it on all ports except the port on which it was received, which is port P. Now suppose if this forwarding table was looked at and it says that this D is on port P and this was the same port on which this particular frame was received, then you don't have to do anything. You have to drop the frame. This corresponds to the case earlier where host A sent to host B and this was received on port 0 of the bridge, and it knows that B is on the same port, so it doesn't have to do anything. It just drops the frame. Now the other case is if entry for D in the forwarding table corresponds to some other port I which is not equal to P, then you forward just on I, not on the other ports. Very simple algorithm. The beauty of this is that it permits a plug and play operation, and this is very desirable when you are administering networks. You don't have to change the hardware software in the host. You don't have to do any manual configuration in the switches. All you need to do is interconnect the segments or the host through switches and you're done. The switches manage everything. Another point I wish to emphasize is that this learning process is an optimization. It is not required for correctness. You can always employ the strategy of sending out on all ports other than the port on which you received a frame. So when I covered this bridging, I have used some topology like this where LANs were interconnected through bridges like this. But you don't necessarily have to work with the LAN. You can even interconnect hosts like this. In fact, this is how the current Ethernet works. And the same concept works well even with this. That it will work, I will leave it for you to work it out. So Ethernet switching is rather cool. So are we done with this? Well, things are never so easy in life. This interconnecting with bridges can run into issues if certain things happen. If your extended LAN topology has a loop, then you run into problems. What those problems are, I will get to that shortly. But why will such loops happen? It can happen because of misconfiguration. When you are interconnecting many LANs through bridges, often a network administrator has a scope of his own LAN and interconnection with the bridges. He doesn't have the overall scope of how these LANs are being interconnected elsewhere in the particular network. So loops can creep in. Often redundancy is deliberately added for fault tolerance purposes. For example, in this particular case, if this bridge were to fail, you still want the LAN segments to have a path to talk with each other. So that way you can send it in this particular fashion. Earlier, maybe host A talked with host B via bridge 1. In case this failed, it should be able to talk via bridge 2, bridge 3. So such loops can happen as part of the network topology. Then what is the problem when such loops happen? Let's see through an example. Suppose host A sent a packet to host B. So this I'm representing like this. Now assume that these bridges have empty tables. They don't know where host B is. So this packet is received by bridge 1 as well as bridge 2. We'll focus on bridge 1 first. So it received here. So this, it came on this port. So it will send it out on the other port. So now through this, bridge 3 is going to receive the packet through this port 0. Again, it received on port 0, so it's going to send it out here. And now this packet is going to come to bridge 2 on port 1. It received on port 1, so it is going to send it here. Now again, bridge 1 is receiving this packet on port 0. It doesn't know where B is, so again it is going to send. So as you can see, there is a frame that is going to circulate like this because of this loop. Similarly, when host A originally sent the packet, bridge 2 is going to get, and this is going to send the packet like this will go like this, and this will go like this. So there is one frame circulating in this fashion through bridge 1 and another frame circulating in this fashion via bridge 2. And these frames can loop indefinitely. You don't want that because it wastes the capacity of the Ethernet. So how do you solve it? We will cover it soon. So here is a summary of what we have seen in this video. Ethernet switching extends LANs to form what is obviously called an extended LAN. This can interconnect a few thousands of hosts. The very nice thing about Ethernet switching is it supports a plug and play mode of operation. So there is no manual configuration of switches involved, no hardware or software changes at the hosts involved. This learning is a very nice feature that switching supports, which improves efficiency. And this switching can fail if the network topology has a loop in it. Now, how to solve this looping problem? We will see a solution in the form of spanning tree in the next video.